Welcome back to the Reko live coding stream. Today we're going to finish off the work on the rewriter that we started last time and finish up with a few bug fixes along the way. The focus now will be to try to get as much of the subject program scanned as possible using our rewriter, and the way we'll accomplish that is by iterating on missing instructions and implementing rewriters for them as we encounter them. Recall that last time we implemented load, which is a very simple instruction. We have a few others that are a little bit more complex, in particular the ones that have different condition codes depending on which of the various addressing modes that are being used. For instance, the add instruction has 5 variants, and some of them have different flags set as side effects. For instance, the one where you add a register to an immediate value sets the 0 flag. That does not happen when you add an immediate value to the stack pointer. There, the 0 flag gets cleared. So we'll go through these as we encounter them in the binary until we get to a point where Reko actually finishes scanning. At that point, I will conclude work on the stream, but I will finish it up offline. Hopefully we'll get most of the interesting instructions here. So we're going to try to hunt down and finish all of the addressing modes of the processor. So, simple way to do this then is to just launch the program. Remember that this function emit unit test will get called every time we hit a function that we haven't implemented yet. We will also hit exceptions when we hit addressing modes that have not been implemented yet. So we will use the unit tests and these exceptions to guide us in the implementation of the rewriters. So last time we implemented no-up, we implemented jump, and we implemented load. And clearly there's going to be a few more that are going to be interesting. I expect add, XOR, and OR to appear, call, of course, and we will probably want to handle conditional jumps as well. So we build and we launch. So here's our program. As before, we scan and we don't get very far. And the reason for that, of course, is we haven't implemented anything. So let's try to see the place where we failed is going to be in this file, gameboy.test. In fact, I'm going to open that in Visual Studio Code so we have it available for quick copy and pasting. Okay, so the first instruction we are going to handle now is XOR. And XOR is a well-known CPU instruction, and of course it has an equivalent in both C and C++, but also in the RTL language that we talked about yesterday. So what we want to end up doing is implementing rewrite XOR, but we also want to use the unit test as a guide. So we'll take the unit test that was generated and paste it into the unit tests file for the rewriter for this architecture. So we'll paste it right in here. And so let's see what we expect XOR to do. Well, if we look at the manual for XOR, we'll see that it sets the 0 flag and then clears all the other flags. And we also know this from the actual rewriter itself. All the 3 variants do the same thing. They use this. So we only need to check for one particular pattern of XOR. That saves us some work. So what does XOR do? Well, it always implicitly uses the accumulator. So in this case, when you say XOR A, you're actually doing A equals A XOR A, which is an idiom on this processor to clear the register A. Then of course we need to set our flags, and so that was Z and then 0, 0, 0. So we expect the 0 flag to be set to the outcome of the XOR operation. So we'll write that as cond A, and then we need to clear the other 3 flags explicitly. So that will be N equals false and H equals false, and finally carry equals false. And that ends up being 5 instructions, and we change the address. So let's see if that passes. Let's try running that unit test. And while that is grinding away, it's going to fail, of course, because we haven't implemented it. We're going to go to the actual implementation here. And we realize that these two are setting the same flag, so we don't need to keep separate versions of XOR. So we'll clear that out and this comment. And then we will say we need the accumulator. So we'll say var accumulator equals, and then we'll go to our binder and ask for a register. That's the accumulator. And then we'll have the source operand, which is going to be operand 0. We only have one operand for the XOR instruction on the architecture. And then we need to perform an XOR. So we'll say assign to the accumulator the result of XORing the accumulator with the source. Right. And then, as a final step, we need to emit a condition code based on the outcome of the XOR instruction. And this is the idiom for doing that. So we take the register, which is the result, and then we use cond to express that we are interested in the outcome of that operation, and then we bind that to the Z flag. The other flags will be set to 0. We can quickly review how that's done, and you can see how that's done here. So we set the expression to the Z flag, but the other ones are being set to 0 or cleared. Alright, so let's try running the unit test now and see if that passes. It's possible it won't, but at least we'll get closer to where we want it to be. Oh, and that makes me realize we have to actually, in our big switch statement, call the XOR. And we don't do that. In fact, what I'm going to do is I'm going to go to the mnemonic definition for all of our instructions. And we're just going to write the whole dispatcher straight away. So we don't have to do this piecemeal, because it's very mechanical and boring. So what we'll do is we'll take this to here. And now what we're going to do is we're going to just do a replacement here where we replace each one of these instructions with a case, and then the instruction itself. And let's do that. And this is what we'll paste into the switch statement in the rewriter, and that way we don't have to fiddle around with those anymore. We still are on the hook to for implementing all these, of course, but we'll end up with a bunch of duplicate errors here because we've already implemented a few, so we'll just remove those. We already have them working. Okay, we're good to go. Let's try this again. And we have a green dot. Perfect. So now we'll resume our scanning. We'll try the next. And it's going to continue progressing step by step until we start branching, when we have multiple threads of disassembly going on after the branch. And that will speed up our progress. So let's scan again. Boom. Okay, so this time we hit an unimplemented operand type, doing a load. Okay, so let's take a look at that load. The load was a load stack pointer with an immediate value. So now we need to translate immediate values. Well, that's easy enough. Immediate values are, and hopefully we got a unit test maybe. Let's check that. Okay, so we have a unit test for an immediate. So let's just grab that because we'll want to replicate that. I'll make sure we don't regress, and we'll put it here. It's a simple load. So what should a load do? Well, loads have no bits set as far as I can. Let's verify that. But yeah, actually we did verify that earlier. Load does not set bits. So here, all we want to do is say that the target register should have the value 0xe000, and that's a 16-bit quantity. All right, so now we will implement the support for immediate, which is very simple. It's just the immediate operand already contains the value that we need. So all we need to do is say im.value. Value is the immediate value, and we're good to go. So let's run that again. And hopefully we'll pass that test as well. The pace will pick up as we proceed. Perfect. All right, next instruction. So we're waiting for those branches and calls. Those are the ones that we're looking forward to, because it will expedite this. All right, next. All right, we hit a memory operand. This will definitely be exciting. And it's a post-decrement operand. This one's going to be a little bit complex. Let's see what the unit test is. Okay, so this is a store of the accumulator A into the memory pointed to by HL, and then a subsequent decrement of HL. So let's write the unit test first, and then implement the code for it. So what we would expect this to do is to, well, we want to remember the initial value of HL. So we need a temporary variable, and I'm going to call it v question mark, because the actual number for the temporary variable will vary. I don't know what it will be, but it will be some temporary variable that we generate in our binder. And what we'll do is we'll take the value of HL, so we remember that. And then what we do is we assign the memory address of HL. Actually, maybe we can get away with not using HL. Let's try. Let's see. Yeah, you can do this. Oh no, we can't, because this is right. Okay. You will notice why this is not possible. We'll definitely need to introduce a temporary variable. So let's call it v question mark, and that's going to be getting the value of HL as it is now. And then we're going to increment the value of HL. And because we are using HL as a pointer, we definitely know that this 1 is a signed integer. So we can make it a signed integer by putting an I in front of the sigil here that indicates what type of constant this is. So that implies that the 1 there is a signed integer being added to a pointer. Alright, so now we've incremented HL, but then when we then perform the store, we want to use the temporary variable as the pointer. So we'll use v question mark here, and we're storing a byte, and that gets set to the value of A. So that should do the job. So this is what we want to generate. So now we need to write the code to do this. So first of all, we need to create an assignment to a temporary variable when we're getting one of these So we'll have to detect the case. We're doing a memory operand. And we have to check to see whether we have a base register, because otherwise we will not have a post decrement. So if the base is not equal to null, then we're in here. If there is a post decrement, then we have to remember the we have to make a copy of the effective address. So let's start by creating a variable called effective address and bind it to the base register. Alright, so now we have an identifier for it, but now if we are post decrementing, and in fact post incrementing will look very similar, we will need to create a temporary variable. So we'll create a temporary variable, and let's make it the same type as the effective address. And then what we'll do is we'll create an assignment to the temporary variable from the effective address. And that's what that statement is. Then we're going to increment the effective address. And there's a special, in our RTL emitter, there's a special method for adding signed integers. Recall that we determined that that has to be a signed integer because the HL, or the effective address, is a known pointer. So we'll take the effective address and we'll add -1 to it. That's a decrement. Okay, and then we will make the effective address be temp, like that. So now what happens is this is going to be used in the construction of the memory access operation. So then we say, let's put a break down here first. We will say return, and then we create a memory access. And the memory access is of data type memory.width, and the effective address is EA, like so. We need to say the data type here. Okay, so with a little bit of luck, that will also pass. And recall, this was the instruction that did not match with the Z80 encoding. This is a very Game Boy specific instruction. Does not exist on a Z80 machine. Okay, so we get an error in our unit test. Let's see why. I have forgotten to correct the address in the auto-generated unit test. It's easy to forget. And of course we're expecting an error here. We're expecting the temporary variable to have some other index other than question mark. We'll find out shortly what that is. Let's see. Alright. We need to adjust this as well. Slow going. V4, fine. So we'll make V4 the variable that we're setting. So this has the correct semantics. We hang on to HL, we increment HL, and then we also assign or store to memory using the old value of HL, which is the same thing as implementing a post increment. Now the order of these instructions can be reshuffled in later stages by the decompilation. So we're good to go. Next, another memory operand type. This time it's an absolute address. So here we're accessing an absolute address. So this is the else case. And let's grab onto the unit test while we're at it. Notice here we have now 3 unit tests to implement. That's good. So let's make sure we put them in our test file. Well, let's do them one by one. So decrement, well, decrement is b is going to be b equals b minus 1. And that's going to be an unknown 8-bit quantity. We don't know whether it's a signed one or an unsigned one at address 0. But we do know that dec has side effects. Let's take a look at all the different flavors of dec that we have. So sometimes dec sets the condition codes here when you're dealing with a 8-bit quantity, but when you're dealing with a D word, it does not set the any other flags. So we need to write another unit test to capture that, because otherwise we'll introduce an error. So let's see what the dec opcode is for a register pair. There's dec DE, which is a 1x or hexadecimal 1B. So let's write another unit test real quick for decrementing a register pair. So if we have a register pair, then there will only be one instruction, a 16-bit decrement. But for the 8-bit decrement, we need to set the output flags. And so let's consult the flag we're setting, the 0 flag, and then we're hard setting the N flag to true and then H flag to the outcome. So we're expecting something like this. The Z and H bits are set based on the outcome of B, and then the N flag is set to true, I guess because the subtraction has just occurred, and then the C flag is untouched. So here we have 3 instructions, not 1. Alright, we might as well hit the next instruction, which was a what was it? Was yet another load, but this was a load with an absolute address. So we need to implement that version of the memory operand case here. So let's fix that. So in this case, we need to create an absolute address. So we'll say var effective address equals address pointer 16, a 16-bit pointer of the memory offset field. That becomes the address that we want to access. But that's an integer, and we need to force that into an unsigned short. Alright. And then we're good to go. We say return m.mem, the memory width, and the effective address. And now we notice that there's some duplicated code. How about we move this down here, make effective address a local variable called EA, and then the 2 different branches will just make sure that EA is correctly assigned before returning. Okay, that's good. We haven't implemented post increment, but we might as well do that now. We'll probably won't need a unit test here. I'll try to be very, very careful here. I'll just say post increment, and then instead of subtracting 1, we add 1. Otherwise, same semantics as post decrement. And naturally, these 2 should never happen. We already have an assertion that makes sure that both of these 2 bits are not set simultaneously. But then we see a little guy called JR. Now JR is a conditional branch, and what we want to do now is capture the essence of a conditional branch, which is it tests a condition code and then has a branch destination. So we need to convert this operand, which is a condition code operand, into a test expression, which is another low-level register transfer instruction that we have that abstracts the notion of condition codes. In a C program, the target of our decompilation, we cannot have condition codes. So we do what we can to try to get rid of these condition codes. So what we'll do is we'll have something that looks something like if we test for not 0 on the 0 flag. So what we're doing here is we're saying if the condition that we're expecting is not 0, and the variable that we're testing is the z bit. So we're expecting the z bit to have been set by a previous instruction. So if that test succeeds, then we have a not 0. And then we can go to some offset that we don't know. Now this is a transfer instruction, so we expect this to be a t. And recall that our disassembler is supposed to set the transfer bit as well, and it wasn't. So I'll put a t there to make sure that we get that correctly. This, on the other hand, the load is it's a store. We're going to do a store to the absolute address cbb7, and that's going to be a pointer, a 16-bit pointer, and it's storing a byte, and the byte is coming from A. Alright, so now we have a bunch of unit tests that we hope will pass. Alright, so let's see how that goes. Well, we haven't implemented jump relative yet, and we haven't implemented dec. So let's get those implemented. So let's find dec. Dec first of all. So dec. So we need to check then if we are 16-bit or not. So we need the operand. So let's get the thing that we're decrementing. That's the operand rewritten. And if the operand is 16-bit, so if exp.datatype bit size is 16, then actually when it's not 16, then we will set the flags after the decrement. Otherwise, we're good. So we tell the emitter, please assign to exp the result of subtracting 1 from exp. And in this case, I cannot use the signed add subtraction because I don't know whether the thing that I'm subtracting from is a pointer or an integer or what. So we have to fall back to the most general form of subtraction, which makes no assumptions about the type, or rather it makes the assumption that it's some entity that can be used in an integer subtraction, but it's not certain whether it's a signed integer or an unsigned integer or a pointer. And the quantity we're subtracting is 1. So there we go. And then if we are 16-bit, then and only then do we emit the condition code. And the condition code is, as usual, cond of exp, the thing that was just mutated. So that would implement all of these cases. All right, great. Let's find JR. Now JR is interesting because JR has 2 modes. It has one mode where it takes a condition code. So those are the conditional relative jumps, but it also takes a unconditional mode where it has no condition code. So we need to check for that here. So let's do that by checking the number of arguments. That's pretty easy. So if the instruction.operands.length is 2, then we are conditional. So then we know that the first expression is a conditional. So we'll just have op convert that for us. So var condition equals op 0. And then we know that the second condition is going to be an address. So we'll say destination or target equals, and we'll just cast, because we know that the second operand is supposed to be an address. And then we emit a branch on the condition to the target. Otherwise, if there's only one operand, then the target is the first operand, and then we do a go to that destination. Alright, that should do the trick, but we need to implement the test for condition codes. So let's see, so that was inside of op. So op might receive a condition code operand. And so now we need to handle that. Alright, so now we need to take a look at the condition code that was set inside of the condition code operand. So we need to switch on the condition code. And we're going to implement all of these at once because there's so few of them in this architecture. The Z80 has considerably more, but on this instruction there's only 4 possible conditions in our jump and return and call statements. They are Z and C and NZ and NC. So there's only 4 cases we need to take care of. So let's just implement all of them at once. So if somebody said jump on carry set, that means that we need to test for well, carry bit set means that a subtraction occurred and something became greater than or equal in general. Sometimes, of course, it means that the word overflowed, and we will handle there are parts of Reko later that handle that distinction. But basically, if you subtract 2 items, the resulting condition code is a less than, unsigned less than. And the expression that we'll be testing is going to be the Z flag. So we need to grab the Z flag and make it into a variable. So we go to registers.z, and then we say binder, no, C, not C, binder ensure flag group. Okay, and then we'll do the same thing for no carry, except we invert the tests. If this is the case, then we're unsigned greater or equal. And then we do the same thing for the 0 flag. And in that case, if it's 0, then it's equals, not equals. Let me fix the unit test as well. Alright. Great. So that takes care of the jump relative. And we did the absolute absence, so maybe these will all pass. With some luck, they will. Nope. We forgot the break at the end of the case. Now that's better. Let's run the tests. Okay, so here's the bug in the disassembler. It's not treating relative jumps as transfer instructions. So let's fix that. Yeah, indeed. So here is the unconditional transfer. And then we have the other conditional transfers. There's 4 of them. All right. And here I forgot to fix the address, and here I had an error in my unit test, but Fortunately, that was caught. All right, run them again. We iterate until we have a green bar, and then we will continue. And we keep harvesting new instructions as we traverse more and more of the binary. Alright, still getting errors here. Okay, so this is me making plenty of mistakes. Good thing that I have these unit tests in place. Although this is incorrect. It's supposed to be a NZ. So let's take a look at the diagram to make sure. 2.0 is indeed NZ. So why are we seeing... It is NZ. So why are we... Oh, copy and paste, of course. Copy and paste. Your greatest friend, your greatest enemy. It's looking at the wrong bit. Alright, that fixes that. And then the post decrement, I forgot that little squiggle 0. There's a reason behind that 0, but I'm not going to bring it up right now because it involves some completely different parts of the disassembler. Or decompiler, sorry. So we'll take that up at some other time. For now, just be aware that all of memory accesses are using that operation. Okay, so here we have a backwards branch. That's nice. We were able to handle that correctly. FC should go to FE. Yeah, that's correct. Okay, we're good to go. I'm pretty sure this will pass now. So now we iterate again, and hopefully we'll harvest a few more instructions now that we have a branch as well. Although that was a backwards branch, so it might not uncover new instructions. We'll see. So load and scan, and it's done. Okay, we got a few. All right, this is good. Now there's a lot of them now. So these are going to be we're rapidly approaching sort of the majority of the different types of instructions encountered in a typical program. So we've ran across a call. Now a call, it's a transfer instruction, and it gets translated to the RTL instruction call, and then we're calling a particular address, 33DF, and on this processor addresses are absolute. So what you see there is what you see here. Okay, so here is an interesting one. Here we are loading from an high. It's the load high instruction, which loads from the addresses in the interval between address FF00 and FFFF. And what this instruction is supposed to do then is actually add 42 to FF00. So we need to change our memory, the logic that translates memory accesses so that it detects that special case and then adds an FF00. Let me confirm that FF00 is in fact the correct. Yes, it is FF00. Okay, great. So what we'll then need to change this to is a store at 0xFF42, and that's a pointer, a 16-bit pointer, and we're storing a byte like this, and no flags are set by the LD function. Here we have the opposite of the disable interrupts instruction that we did last time, so we'll just implement that straight away. And again, the address needs to be cleaned up. Now push. So what does a push do on this processor? Well, it first subtracts 2 from the stack pointer, and then it stores a value at the location of that new stack pointer. So this is going to be 2 instructions. And so the first thing we do is we say adjust the stack pointer by 2. And again, because we know this is a stack pointer, we're going to decrement it by a signed integer, not an unsigned integer. And then we store. So at that location, we store the pushed value. And then we run it across compare. CP is compare. Now compare on this processor is the same thing as performing a subtraction, and instead of saving the subtraction, the result of the subtraction, you only care about the condition codes that are set in the processor bits. And if we go back to our CP definitions, we'll notice that they all set. Okay, interesting. So they set 3 of the flags according to the outcome of the subtraction, and then they always set the n flag to 1 or true. So we need to write that in our code. So the Z and H and C bits are set to the outcome of, and of course CP is an implicit use of the accumulator A register, so we'll need to write something like this. That is, subtract the 8-bit value 1 from the accumulator, and whatever the flags of that that result from that operation, store them in ZHC, but then also set the n flag to true. And this we'll need to fix as well. Make sure the addresses are correct. So this is 2 instructions. Okay, now here we have a conditional jump. So it's going to be very similar to the conditional relative jump. The only difference is that the operand is absolute, but the disassembler has already disassembled that correctly for us. So all we need to do here is just make sure that it's a transfer function, and that we write it like this: if test equality on the Z bit is true, then we branch to, and again this is an absolute value, 492. And we have finally an add instruction. So here we're adding 2 to the stack pointer. So here we have to be careful because we have so many different flavors of add. This one, when you add, oh, this is awkward. Let's see. So if you add SP with a immediate value, then the following bits are set. But if you add 2 register pairs, then the following bits get set. And finally, if you add an 8-bit value, these bits get set. So there's all kinds of different bits being set. So we have to be very careful when we implement this. We might as well implement all of those add instructions at once. So this is add SP immediate. This is add a register pair. And then finally add, and this would be 8-bit value. So in the case of SP plus a constant, we will set the HC flags and then clear the Z and the N flag. Alright, so HC, first we perform the sum. So SP equals SP plus, and this is a signed integer. We know this from the disassembler. So it's going to be a 2 signed 16. And then here we will implement, oh, I'm in the wrong place. This is wrong. This is for the register pair. And then we add Well, we need to test HC. They're the condition of this beast, and then finally we have to set the two other bits, Z and N, and they were both false. But when we're adding a register pair, and so now we need to find a nice register pair add instruction, and I think we have one right here. The 09 is a add HLBC. So let's write a test for that. So HL equals HL plus BC. And in this case, the bits that we set are HC again, but we only set the N bit to 0. We don't touch the 0 flag here. So we can copy this. We'll need to fix up those indices. But here, actually we don't set the Z at all. So that's going to be that. And then this is going to be that. All right. And then finally for our 8-bit, we'll need to find an 8-bit add. Those should be fairly easy to find. Here's one, add AE. That's instruction 8.3. So that would be A equals, in wrong place, sorry. Here we go. So this is going to be add AE. And that's going to be A equals A plus E. And then we just set the flags. In this case, it was ZHC. And then clear the N flag. ZHC equals cond of A. And the N flag is false. All right. And let's fix this address. And the instruction count, address, instruction count, address, and instruction count. So now we've implemented all the different variants of add, or unit tests. We haven't implemented the actual code for them yet. Increment, well, that's another one that has possibly multiple flags being set. So we increment a register pair, no bits are set, but if we increment memory or a register, bits are set. Okay, and it's going to be the ZH flags are set to the result of the increment, and then the 0 flag, or the N flag, gets cleared. So in this case, there are no flags being set. We just say SP equals SP minus 1. And here we don't know whether the stack pointer is being used as an actual stack pointer or not. So we can't assume that that integer is signed. And that's it. No more work for you. And let's fix the address there. But if we then increment the A register, then that will be, or increment B, that's instruction 4, or opcode 4. That's an increment of B. In that case, we say B equals B, and it's not an increment, it's an increment. I'm off my game. So in that case, then, it was, what bits was it now? It was Z and H. So we say ZH equals the condition resulting from that last decrement, and then the N flag is false. But the carry flag is left untouched. Great. So that is inc. And we have OR. So what does OR look like? OR is is always setting the Z flag and then clearing the other bits. Okay, that's nice. That's nice and regular. So we only need to implement one test. So in this case, what we're going to do is implement OR as A equals A OR, and then memory 0 of HL. Now, that's a byte. And then we set the Z flag to the outcome of that. And then the usual dance with the other bits. So N is false, and H is false, and the carry flag is false. So this guy has actually 5 RTL instructions exploding out of a single OR statement. Let's fix the address as well. This one has 3 instructions, and that one has 1. Alright, so now let's implement these guys. So let's run the test so that gives us a guideline as to what is missing. But we start with add, I suppose. Let's go ahead and do that. Now add always takes 2 operands, I noticed. There's always 2 operands, so what we'll do is we'll say destination is the first operand, and the source is the second operand, and then we create a sum, an integer sum of those 2, and then we have to check to see. So we had 3 cases, right? We had the case where the left side with the stack pointer. So if the destination and we have to test it. So if the destination is a if the storage, well, first of all, that's an integer. We know that it always is going to add to a register, so we can safely cast this to an identifier. And then we will say if the storage is the same as registers.stackPointer and the source is a constant, then we have a sum of a stack pointer and a constant. Then we need to emit these flags after the sum and based on the destination. But otherwise, if the destination data type bit size is 16 bits, then we have to use these flags. Otherwise, we are the 8-bit case, and then we have to emit these ones. Oh, and I got the wrong one for the SP. It should be that. Okay, so don't ask me why they decided to implement it this way, but that's what it that's what the manual says. So we have to go by the manual. All right, so that's add. Then we go to call. We haven't implemented call yet, so let's go to call. Call, and call, it's going to look very simple, I think. We're just going to say call to the destination of the first operand, and we need to specify how many bytes we push on the stack when we make the call, and this CPU pushes 2 bytes on the stack. Some CPUs push 0 bytes. Most RISC processors, in fact all of them, have a separate register for returning the return address, but this architecture stores it on the stack. That's why we have a call with a 2. Then we need to do the compare. So the compare is going to be quite simply left equals operand 1 or 0, right equals operand second operand, and then we emit an assignment of actually let's create a variable called flags, which is going to be the ZHC. Oh, in fact, no, we can use emit directly, because what we'll do is we'll say take the subtraction, the integer subtraction of those two, and compute the conditions from that. Very good. Enable interrupts. Okay, that's going to be very similar to disable interrupts. We can just copy that. That was easy enough. Increment. Alright, so how many increments? We had 2 different increments. Right, so if we're 16-bit, we have to do them one way, and otherwise the 8-bit way, which sets flags. So var expression equals operand 0, and then we do a assign expression 1. That performs increment, and then we check to see if the expression dot data type dot width is 8 bits. Then we also need to set the unit or the bits. So we'll use that. Okay. Bit size. Conditional jump has not been implemented yet. Right, so if the operand length is 1, then we do a goto, but if otherwise the operand length is 2, so then we say the condition is operand 1, the first operand, sorry, and then the destination or target is the address to which we're jumping, and then we do a branch of condition to target. Good. Load high. Okay, so this one is a little tricky. Here we have to, when we generate the operand, we have to pass in a flag to the converter that generates these operands from the addressing mode to indicate that we need an FF to be added to it. So the way I do that is I go to the function op, and we pass in an optional bool. What do we call this? High page. By default it's false. So if we receive a mem of a constant and the high page is set to true, then we want the offset to be adjusted. So if high page is true, then offset we'll need to add, and then we use that here. Now we have to implement LDH, which doesn't set any condition codes as expected, but it does. We do need to set the high bit when we're accessing memory. So we'll say var source equals op1 true in case this is a load, and var destination is op0 true. Notice that that true flag will only affect the if the operand is a mem or memory access. If it's a register access or an immediate, nothing will happen. And then we perform the assignment, like so. Nice. And then let's make sure the unit test is sane. Yeah, well, we did already, right. Okay, then we have OR. Oh, this is interesting. OR is only emitting 4 instructions. Now, why would that be? Have we already implemented OR? I'm surprised. We have not, so that means that our B6 is not getting turned into an OR. So that needs to be debugged. Let's save that for later. Let's take a look at push. Push has not yet been implemented, but push is easy to implement. First, we need to grab a stack pointer. We ask the binder, please give me an identifier for the stack pointer. We will then subtract 2 from the stack pointer, and remember this is a we know this is a signed subtraction because stack pointer is being used as a pointer here. So we subtract 2 from it, and then we store, and this is going to be always a 16-bit value because it's a push on this processor. And then we take op 0 as the thing we push. Nice. Okay. But something is wrong with OR B6. Now B6 should have been disassembled to an OR. So something went wrong. So let's debug that by putting a breakpoint in our rewriter at the point where we enter here. And let's see why we're not getting an OR. We should be getting an OR. So this is a what instruction? It is an OR. Oh, my bad. We actually have to implement the OR instruction. It's late for me. It's been a long day, making lots of mistakes. Thankfully, I have this wonderful debugger that helps me as well. All right, so we need to, first of all, we need to generate an accumulator. So the accumulator is, we ask the binder, please give me an accumulator. And then the source operand is the single operand of this instruction. And then we have to update the accumulator with the OR of the accumulator and the source operation. And then finally, we need to update the condition codes with the same value, or with the outcome of the accumulator. Nice. All right, so that was OR, and now let's try running all the unit tests to see if some of them pass. We have 12 failing tests currently. Down to 6. Right, copy and paste. Copy and paste. Okay, interesting. We've decoded that as a signed. Yeah, so this is tricky. If we are adding a value or two values together, Reko makes assumptions that the two values in a sum, an integer sum, have the same bit size. We do not automatically do the promotions that a higher level language that C++ or Java or C# would do. So we really have to convert that number into a wider value. Fortunately, that's not too hard. We already are checking for that case. So let's go to the rewrite add and check for the. So yeah, so let's just do this. If this is a constant, we're going to have to modify. Yeah, we'll have to move this into all the 3 branches. It's regrettable, but not too horrible. But here, before we perform the sum, we have to widen it. So we have to say source equals constant, and we know it's a signed number, so we'll just say int 16 of the constant C to int 16. So what we're doing here is we're taking the source operand, the second operand of this addition to SP, converting it to a signed integer, a C# integer, and then wrapping it up inside of another constant, and then doing that in the assignment. And that's because we have to keep the 2 operands of the plus or the addition expression. They have to be the same bit length. Call. Okay, here's another bug in our disassembler. The disassembler should be marking calls as transfer functions, and it's not. In fact, it's a bit more complicated than that, because we need inster class transfer or inster class call. And then we have a conditional version of these calls, so we're going to need to make them conditional transfer or call. Like that. And let's find them all. There's the next one. And there's another one. And there's the 4th one. Okay. Compare. Blows up. Why? Is it possibly an implicit operand? Let's find out. Compare. It is implicit. Okay. So the first operand of the CP instruction is always the accumulator. There is no second operand. So right is actually op0, and left is binder ensure register registers A. Nice. Okay. And one more, the push. Ah, yes. Whenever you're accessing memory, you have to specify how many bytes or bits you are touching. So let's do that. Alright, we're almost done with this batch of unit tests, and we should be seeing a lot of instructions. But we haven't bumped into and or sub yet, so those will clearly need to be addressed. But it is converging. Okay, 5 errors. That's a bug in the add implementation. So let's find add. Go there. Ah, yes, of of course, these are all need to be wrapped in a cond. Again, the cond is a summarizing, sort of hand-waving abstraction that hides the nitty-gritty details of the actual bits. Otherwise, we would have had to written 3 separate assignments here, which would have exploded the code even more. Same idea here. This is actually HL, and so we just fixed that. And for this one, we fixed that just now as well. The call now. All right, so the call is at the wrong address. Let's fix that. And then the compare also needs to be wrapped. So find compare. So we do need to put a cond on it. Like so. And now, hopefully we have a green bar. Oh, almost. Ah, yes, we need to annotate that we eat 2 bytes of stack when we call the call. Okay, so I'm going to now run again, because I know that's going to pass now. This unit test will pass. We will now try to collect a few more instructions in our scan. Let's get rid of the breakpoint. And we've blown up inside of... Ooh, very interesting. We've hit... I need to take a look at this. What are we doing? We're actually outside of... I'm going to skip this exception for now. But we're clearly hitting some new places in our code. Okay, that was interesting. And we've also discovered that we can't treat the right-hand side as an identifier, because we're apparently adding immediate values to memory, or a stack pointer to a memory location. But this, is this correct? I'm not sure if we actually have that encoding. That might be a disassembler bug again. We do have HLSP. So I think that's actually a bug on the disassembler on instruction 3.9. That should be an add HLSP, which it's not. So we need to fix that. So 3.9 add HLSP should be add HLSP with no memory to reference. Let's make sure that that indeed is a bug right now. But here there is no memory to reference, so there shouldn't be in the disassembly. And let's see if we gathered any more instructions. Sure we did. We got a return, an and, shifts, but no new in opcodes. So what I'm going to do actually is I'm going to stop right here, because we're not making any new learning points. It's mostly tedium from now on. with the possible exception of subtract with carry. Most of these other ones are either going to be implemented as very similar to what you've seen before, where these operations that correspond to side effects will be using the side effect RTL instruction to model them. Returns will be modeled with a return instruction. I suppose we can do a few of these, but I don't want to bore the audience with all the nitty-gritty details of this. So what I'll do is I'll do a couple more, but then it will wind down and I will provide the remaining instructions by tomorrow. And then this will be available as a finished rewriter for this particular architecture. But let's do the sort of the interesting ones are going to be the return, and pop, I suppose, is interesting, and add carry is interesting. And subtract with carry will of course be related to that. So first of all, let's just verify that added. Yes, so we've verified that was a bug. We can easily fix that in the disassembler at 3.9. So this is supposed to be that. Much better. Okay, so let's add these unit tests for the final instructions that we'll be doing tonight. So there's the return, and this is a conditional return. That's exciting. So that will definitely be an interesting case to see how that gets implemented for conditional instructions. Let's go back to the unit tests. I'll do pop. We will do let's do the add with carry. Let's stick with those. I'll restrict myself to them. So, so this is a conditional return, which is interesting. It's very specific to the 8080, 8086, 8080 and Z80 and this Game Boy processor. A conditional return. This was not used in the 8086 family. Intel dropped support for that. So it's a little wart for these particular CPUs, and apparently it was important enough to include in the opcode set, consuming 4 valuable slots in the instruction set to do a conditional return. So this runs. We run into a little issue here because the RTL language that Reko has does not have conditional returns. It only has conditional gotos. So in order to implement return NC, we have to implement it as a jump around a return, and the jump would be on the inverse of NC, that is C. And let me show you what I mean. So rather than saying if NC return, we would have to say if test, and the inverse of NC would be unsigned less than carry go to, and then we would have to go to the address after the instruction in question, which would be that address. And then here we have another transfer instruction, which is the actual return. And the 2 and the 0 will be explained shortly. So what you see here is a jump that jumps around the return if the condition NC is not true. So that's how we implement that return. A pop that's going to be analogous to the push. We have two instructions. The first one loads the value, HL, gets the value of whatever's stored at the stack pointer, and it's a 16-bit word. We have no idea what it is, if it's signed or not, or a pointer. And then we have to add to, and this is a signed value. Okay. Now add with carry, we have to implement as follows. We say A equals A plus D plus the carry bit. Simple as that. And add with carry only exists in one permutation. It sets the ZHC flags and then it clears the N flags. So we have to implement it as ZHC equals cond of A, and then the N flag is set to false. All right. So let's hope that all works. Let's try running all of our unit tests. Almost done. Now we need to implement the pop. So pop, very similar to push. We will the destination of the pop is going to be the single operand of this pop instruction. So we assign, and we also need a stack pointer, of course. The stack pointer is, we can steal the code from down here. So now we grab the value from this stack pointer location, and it's a 16-bit value, and then we have to update the stack pointer with a positive 2. Nice. Okie dokie. Then we have our return. Now the return gets complicated by that conditional factor, so we have to say if the number of operands in the current instruction is 1, then we need to take that condition and invert it, because we need to do the inverse of the condition. So we'll use the invert method of expression, which will create a new expression that inverts the logic. And then we say if that condition is true, the inverted condition that is, then we need to go to the instruction after the current instruction, which is instruction address plus instruction.length. So that skips over this instruction and puts us at the instruction after this one. Otherwise, if that is not, if the condition fails, which in the original instruction would have been that it succeeded, then we are ready to do a return. And we will return and we will say how many bytes we pop off the stack, which in this architecture is 2, and there are no extra bytes popped. Those extra bytes refer to the ret instruction on the x86, where you can optionally return not only the return address but also any bytes that were pushed onto the stack as parameters. We might as well implement the regular case, which is if it's not a conditional return, we just do a return. Boom. And are we all passing now? We need to implement the add with carry. We forgot to do that, so let's go there. And this will be our final instruction that I'll be doing on this stream. And it's going to be very analogous to the add, but with the extra carry flag. So we need to generate a variable for that, or an identifier for the carry, and that is should be familiar. We call the binder to ask it to please create an identifier for the flag group C, which is the carry flag, capital C. And then we need to create a variable for the accumulator, which is also I think the add carry instruction actually explicitly states that it's adding to A, right? So we'll say that the left side is operand 0 and the right side is operand 1, and then we want to emit an assignment where we add to the left side the right side, but then that needs to be incremented by whatever's inside the carry bit. And then we need to set the condition codes. And now we run our unit tests, and hopefully with a few more iterations we have implemented these final instructions. Let's see how this turns out. Nope. Another bug, the disassembler, we need to set the fact that these are transfer instructions. So let's go to the .rets. This guy's marked as a transfer, but this one is not. Wonder why that was. In fact, this should also be marked as conditional, because it's a conditional return. It's not a unconditional return, and same thing goes for the other 3 returns. Let's find them all. There they are. And the last guy. Okay, there was another instruction that failed. That was the add with carry. Copy and paste. Let's fix that, and then we're good to go. Still an error. That's a space. Now we're getting picky. And it should be a branch. Oops, my mistake there. I'm definitely getting tired now. So it's a good time to pause after this and sum what we've done. All right, we have a green bar. Let's run through all the tests just to make sure. but I think this is a good place to stop. So what we've done here is we've implemented quite a few instructions now. We have about almost 24 instructions that are implemented. There's a few more, and I will be implementing them on my own time. I don't wish to bother and bore my audience with more of these, but I hope that I've illustrated the gist of how implementing the rewriters is done. It is a little bit tedious. It's hard to do mechanically, although we have been using some tools and tricks to sort of make this as expedient as possible. But in the end, you will find that you'll be consulting the manuals for the respective processors a lot when you implement the stages. It is important to model the behavior of each instruction accurately, though, because the later stages of the decompilation process are dependent on making sure that, for instance, that the condition codes that are being set are being then tested appropriately in the branch instructions that might be following. So, as promised, there will be a update to the project with the final rewriters for this, and by that point, this sample binary should be fully scannable with Reko. Then, of course, comes the exciting parts, which is dealing with the strange warts of this particular environment or machine. Now, the machine has very exciting banking modes and very odd ways of performing the banking. If you read the manual, you'll see how writes to a ROM are actually picked up by a memory controller and translated into a bank operation that switches banks. And how to automatically handle that in Reko is an interesting proposition, interesting question. And I'd love to discuss that with you on Discord if you are interested. Becomes more and more of a niche proposition, though, as we delve deeper and deeper into the sort of the particulars of this architecture. But to all the watchers, I will now say good night, and as usual, I invite any questions or comments. Please send them to Gitter or Discord, or open an issue on github.com. Thanks for watching.